All right, let's talk about a word you hear everywhere these days, from your social media feed to the latest tech news, the algorithm. It sounds kind of complicated, right? Maybe a little mysterious? Well, today we're going to pull back the curtain and demystify it step by step.
So, what is an algorithm really? You hear the term thrown around all the time, usually when people talk about AI or the secret sauce that social media uses to decide what you see. But you know what? At its core, it's actually way more fundamental and a whole lot less scary.
An algorithm is simply a list of steps to solve a problem. That's it. Seriously, the best way to think about it is like a recipe for cooking. A recipe gives you a list of instructions to turn a bunch of ingredients into, say, a cake. An algorithm does the exact same thing for a computer. It gives it instructions to turn an input into an output.
Okay, so if an algorithm is just a recipe, how do we actually write one? Let's follow the journey from just having a simple idea all the way to a concrete set of instructions that a computer can actually understand and follow. It's all about turning a problem into a working solution. To make this super clear, we're going to use one example the whole way through. The problem is simple. You've got a list of items, and you need to find a specific one. This is something you do all the time without even thinking, right? Like looking for a name in your phone's contact list? In the computer world, the most basic way to do this has a fancy name. It's called a linear search. And here is the recipe for that linear search. It's just plain, logical English. Step 1, start right at the beginning of the list. Step 2, check if the item you're on is the one you're looking for. If it's a match, awesome, you're done. If it's not a match, no big deal, just move to the next item and do the same check. And if you get all the way to the end and you haven't found it, well, then it's just not in the list. That's it. This is our algorithm in its purest form.
Now, plain English is great for you and me, but we need to get this recipe into a format that any programmer on the planet can understand without getting bogged down in the specific rules of one programming language. This is where a really cool idea comes in, a universal blueprint called pseudocode. Think of it as a middle ground between plain English and actual computer code.
And check this out. This slide really shows you what I mean. On the left, you've got our simple English steps. And on the right, that's pseudocode. See how it has more structure? It's got keywords like function, for, and if-then that mimic how code works. But, and this is the important part, it's not written in Python or Java or anything specific. It is literally a blueprint of the logic that any programmer can pick up and translate into real code. And this brings us to a really important point. Algorithms are about the logic, not the syntax. It's the thinking process that matters. You can take the exact same algorithmic blueprint, that same recipe, and cook it in a bunch of different kitchens, in this case, different programming languages, and it will still work. The core idea stays the same.
Let's see this in action with another simple algorithm for sorting a list, called bubble sort. Here it is written in Python. Now don't worry about understanding every single character, just get a feel for the structure. You can see it uses a couple of loops and a comparison to put things in the right order.
Okay, now watch this. Here's the exact same bubble sort logic, but this time written in Java. The words look different. You see things like curly braces and keywords like int, but the core idea, it is identical. Two loops, one inside the other, a comparison and a swap. It's the same recipe, just with different utensils. And just to really drive the point home, one more time, here it is in C++. Again, slightly different look, but the fundamental step-by-step logic hasn't changed one bit. This is perfect proof that an algorithm is an idea, a process, that's totally separate from the language you write it in.
Okay, so we can write a recipe to solve a problem. But what happens when there are multiple recipes that all make the same thing? How do we know which one is actually better? This is where we move from just solving the problem to solving it well.
Yeah, this is the critical question, isn't it? Is a faster recipe always the best? Or maybe one that uses fewer ingredients, like computer memory. And we can't just time it with a stopwatch because a fast computer will always beat a slow one. We need a standard, objective way to measure how efficient an algorithm is.
And that standard is called computational complexity. It's just a fancy term for analyzing how the resources an algorithm needs, usually we're talking about time, will grow as the size of the problem gets bigger. We don't measure in seconds, we measure by counting the number of basic steps the computer has to take. The language we use for this is called Big O notation, and this chart gives a fantastic overview. At the top you have O of 1, or constant time. That's the dream. It takes the same amount of time no matter how big the input is. Then there's O of n, or linear time. That's our linear search from before. If the list doubles, the work roughly doubles. Make sense? But then, look down at the bottom. ON squared, quadratic. That's where our bubble sort lives. Those nested loops mean the work grows way faster as the list gets bigger.
And if that table didn't make it clear, this bar chart will. Wow, just look at the difference. The bar for the quadratic algorithm just skyrockets as the input size n goes up, while the linear one just plods along. Choosing the right algorithm isn't a small tweak. It can literally be the difference between a program that runs in a second and one that would take a week to finish.
You know, this whole field of designing and analyzing algorithms is so fundamental to computer science that people often call it an art. And if we're going to talk about the art of the algorithm, well, there's one legendary figure we absolutely have to talk about. This is computer scientist Donald Knuth. Back in 1962, he started writing what he thought would be a single book. That project turned into his life's work, a massive, multi-volume series called The Art of Computer Programming. The first volume came out in 1968, and believe it or not, it is still a work in progress today. It is widely considered the Bible of algorithm. I mean, the series is absolutely legendary for how deep and rigorous it is. To give you an idea, Bill Gates famously said that if you think you're a good programmer, you should try reading it, and that if you can actually read the whole thing, you should definitely send him your resume. It's like the ultimate test.
And here's a fun little fact that I love. Knuth is so obsessed with getting every single detail right that for decades he's offered a personal check to anyone who finds an error in his books, any error at all. The reward? He calls it $1 hexadecimal, which works out to $2.56.
So, let's bring this all back home. This isn't just some abstract academic stuff. The GPS that figured out your route this morning, the streaming service that suggested a movie, the search engine that found an answer for you, all of that is powered by algorithms. And their efficiency directly impacts your life. I mean, what if your GPS used a slow, quadratic algorithm? You'd probably still be sitting in your driveway waiting for it to calculate the route. So the next time something on your screen happens in a flash, just remember the elegant little recipe working its magic behind the scenes. And it makes you wonder, what other recipes are quietly shaping your world?